Okay, today's lecture is very nice because we get to use what we've learned. And what we've learned is that in crystals you have band structure, and the band structure describes the energy eigenstates of electrons living in the crystals. And this lecture is about two types of crystals that are very related, graphene and carbon nanotubes. They're both carbon structures that generate a lot of current research, also some applications in solid-state physics. And with the knowledge that we have at this moment, we can actually work through the math and demonstrate what the band structure of graphene and carbon nanotubes is. So I'm not going to derive it completely for you today. I gave you a handout with the derivation, but we're going to hit the main points of the math and describe the concepts that are behind them. So both graphene and carbon nanotubes are carbon compounds. They're 100% carbon, and carbon is one atom that is worth discussing in great length. As you all know, organic chemistry is based on carbon materials combined with oxygen and hydrogen. That created the entire organic chemistry. We're not going to talk about that. We're going to talk about pure forms of carbon. And we already saw one of them, in particular diamond, a few times appearing during the course. And we saw that diamond has very strongly coupled atoms, and so electrons very strongly coupled to atoms, and therefore it has a large band gap of 5 or 6 electron volts, and that explains why it is transparent to light. We also saw that you can have impurities in carbon that would then give it color. There are diamond color centers. And so we are actually not going to study diamond today because it's an insulator. We are going to look at the band structure of materials that are conducting. And the material that is more similar to what we're going to look at today is graphite. So graphite, like in pencils, is the one that is closely related to graphene. All these materials are called allotropes. So they're made of the same atom, carbon, but they are very different crystal structures, very different physical properties, but the same basic chemical ingredient. And so this slide illustrates the difference between graphite and diamond. Diamond, I already showed it to you. It is a cubic crystal. This is diamond. Cubic crystal with bases, right? And it's a basis where there are 2 atoms per unit cell. It's an FCC, two atom bases in an FCC crystal structure. There is a second atom displaced from the first atom. So this is the basis, and you have the FCC cubic lattice. On the contrary, graphite is a somewhat unusual crystal for us. We did not look at such compounds in detail before. This is what graphite looks like. You have these layers, and inside layers you have chemical bonds shown by these solid lines. And between the layers you have van der Waals forces tying them together. So just intermolecular forces. So as a result, there is a huge anisotropy, as you can see, in graphite. And it is very easy, for example, to separate the layers, take them apart. And that's why pencils write, in essence. So when you write with a pencil, you're just removing layers from the top. Of course, it is more complicated than that, because in your pencil you have a polycrystal. You don't have a single crystalline graphite pencils. That will be maybe a little excessive. But this is essentially the reason why graphite is so easy to peel off and break apart, and diamond is the hardest material we know. Right? So in diamond, all of these bonds are like these bonds here. We will see what they are in a moment. Okay, so graphite it is, and oops. But these are not the only allotropes of carbon. So this is diamond, this is graphite, this is something called Lonsdaleite, which is something in between, because one thing I didn't mention to you yet is that inside these layers you have hexagonal structures. So this is not a cubic structure. It has hexagonal elements here. And this is something in between. So actually, I looked it up. I didn't know about this before. It occurs when meteorites smash Earth. And they have essentially graphite in them. And when they smash, it goes from graphite into diamond. And sometimes it gets stuck somewhere in between. So this is doesn't have a cubic lattice, but it has this trigonal lattice character. But it is a solid form of carbon and not very frequently occurring, but does occur in nature where you have meteorites. Okay, but these ABC ones are things you can hold in your hand. They are big bulk solids in the basic sense of it. These ones down here, D, E, F, and H in particular, are essentially molecules. So these DEF are balls of carbon atoms, and they are called fullerenes, and they are named by the number of atoms. Like C60 looks exactly like a soccer ball, so that's number D. Looks exactly like soccer ball, where you put the sockets of the soccer ball, the vertices of the soccer ball, and where carbons are. But there are also more complicated ones, like C540. It's a huge molecule, 540 atoms, or C70, which has more atoms than C60. So that's very interesting. These fullerenes are very interesting. We're not going to talk about them today, but they've been subject of a lot of studies. Carbon nanotube, we're going to describe in great details. It's essentially one of these layers rolled up. You can generate carbon nanotubes by many different ways, like an arc discharge, a catalyzed growth where you flow methane, which has carbon atoms in it, at high temperature over a metallic catalyst, and methane decomposes, produces a carbon nanotube, hydrogen goes away, and carbon nanotube grows from a metal like a nickel particle. There is also this amorphous carbon. So this is just a random network of bonds, some of them not satisfied, not met, some dangling. Essentially, they're called dangling bonds. So it's a mesh of these bonds, and this is also a form of carbon. So what is graphene? Graphene is a single layer in this layered graphite structure. And this is how it was described to me when I was studying solid-state physics. That, you know, if you could take one layer off of graphite, you would get, that's called graphene, right? Of course, it was not possible back then, but in the meantime, we have found ways to separate and isolate this one layer of carbon atoms, and that's a remarkable achievement, even though if you know how it's been done, it's a little silly. I'll show you in a moment. But this one layer has remarkable properties. For example, it has very strong mechanical properties. So it's 100 times stronger than steel of comparable weight. If you try to break it or tear it apart or make a hole in it, that's hard. Of course, it's usually a very light and small layer, but you can still do this calculation. So it has remarkable mechanical properties. It also has very interesting electrical properties, so transport of charges through it. And we are going to look at some of them, but not all of them in this lecture, right? So some of them that based on your current knowledge of the band structure, but there are, I just want to advertise that there are many more interesting properties in graphene, such as pseudo spin-spin orbit interaction, Klein tunneling, and various interesting things. Okay, so this is how you can make graphene, and it was done by Kostya Novoselov and Andrei Game at Manchester. They took Scotch tape. You can see it here. Apparently, Game's tape gets stolen a lot, so he wrote that it's his. Essentially what they did is they took a crystal of carbon and graphite, and they stuck Scotch tape to it many times, and then they stuck that tape onto a piece of silicon just to have as a substrate, and they stuck it many, many times. And then looking under just a simple optical microscope that you can have in many, many labs, you can see by the color change that you have made a single layer of atoms. So the way it works is diffraction effect. So here is actually silicon on silicon oxide. Silicon oxide is transparent. It's a dielectric. And so you have a layer of atoms here. You have light going through and reflecting off of silicon, which is somewhat of a metal at room temperature. And you have another wave going like this. These two waves interfere. And it changes the color just enough for your eye not armed with anything else, to see the color difference from a single layer of atoms. So thanks to this silicon oxide on silicon substrate on which you can hold. So there are other more sophisticated methods by now of producing graphene, also large scale. This produced little flakes up to 1 micron, 10 microns, maybe 100 microns record in size. Now people can make inches large layers of graphene. It's explored for use in things like flexible screens that you can just pack up and then pull out and read a newspaper on it, things like that, many other applications. So it's becoming an industry, but it all started with a Scotch tape. Now let's go into our stuff that we know how to do. So it's a lattice like this, and each red dot is a carbon atom. Why does it form a lattice like this? Well, carbon atoms are group 4 elements. That means they have 4 available electrons to either make bonds, chemical bonds with other atoms, or to be conducting electrons. And so what happens in the case of these graphene layers is 3 of the electrons participate in chemical bonding with the neighboring atoms, and they are tied in those bonds. So we don't consider them. You can say that they are in the field bands that are way below the Fermi level. This is how it looks. There are 3 of these elongated bonds, and they are sp2 orbitals. They lie in the plane of the graphene sheet. These 3 guys lie in the plane, and they are responsible for making these bonds. You can see that each of the carbon atoms is connected to 3 other atoms, and that's exactly because of these 3 electrons that you have here. All the things that we're going to talk about today are going to be related to the 4th electron. And that electron occupies a pz orbital. Why is it called z? Is because it's along the vertical direction, and it's a p orbital, so it has this figure 8 shape. Those electrons are available for tunneling from one atom to the other, for hopping, and for building a tight binding model with. So we are going to be studying the bands that they create and how they live in those bands. So these p orbitals, the fourth electron of carbon is available for transport. Now, let's start using what we know. A quick quiz. This is the graphene structure. Is it a lattice? Is it a crystal lattice? I have somebody giving some signals. I want all of you to think about it a little bit. You guys should play poker. Okay, go ahead.
I would say no.
Okay, why?
Isn't
You want
lattice just a periodic structure? So I would say yes.
Okay, you say it's a periodic structure, it's a lattice. Was it the definition of a lattice?
I don't know. That's just the definition.
I was just looking at the nearest neighbors. They're not all the
Okay.
same environment.
Yeah, that's very good. So, for example, right, if we look at points, actually I have a bunch of text about it here. If we look at points P and at points R, they have different environment, right? So, point P has two guys on the sides downwards from it and another one higher up, and the point R has the opposite thing, right? So this is not a lattice. Another way to see that it's not a lattice, you cannot come up with lattice, primitive lattice vectors, right? You need to have the lattice vectors to create the lattice. And what is the definition? Is that each sum of two lattice vectors creates another lattice point, and you can take 3 vectors in this direction, 4 vectors in this direction. You always hit a lattice point. And so what could be, you start with this lattice site, what could be the lattice vectors? Well, you have to go to this point and to this point. But if you add these 2 vectors, you're going to be in the middle of a hexagon. There is no atom there. That's not a lattice point. And you're also going to hit, you're going to miss a bunch of atoms this way. So this is actually not a lattice. So there is not a hexagonal lattice, although it is used a lot. These words are, and I will, it's okay to say that it's a hexagonal lattice, but just wanted to make this point that, by our definition, that was not a lattice. What about this? That's a lattice, right? So this, here you can define 2 vectors, and then the sum of them will bring you here. If you go twice in this direction, once in this direction, you're going to cover this entire. So this is actually a triagonal lattice with a basis of 2 atoms. This is what graphene is. So it's a triagonal lattice with a basis of 2 atoms, or you can say that it's 2 triagonal lattices intertwined. And they are equivalent because both atoms are carbon. Both atoms have 3 bonds, so chemically they're equivalent. The 2 lattices are equivalent. You can start with one, and the next one you will find it displaced by the same amount as if you start with the second one. And so you can fill this 2-dimensional space with these kind of rhombical shapes, each containing 2 atoms, as is shown here. That means that this rhombical shape is a primitive unit cell for this lattice. This will be the primitive unit cell. So it contains 2 atoms, and it's a triagonal lattice of these kind of rhombi. You can also define a unit cell to be a hexagon. That also works. You can fill this entire space with hexagons. And in this case, you can also see that it's 2 atoms per cell, because if you count the red atoms and the blue atoms, each belonging to 3 rhombi, and there are 6 of them. So the number of atoms per cell like this is also 2. 1/3 of each atom for 3. So these are now marked A and B. This is, I want to stress it, this is arbitrary. You can also mark them A and B the other way. It just depends on where you start in the lattice. They just marked A and B because there are 2 of them per unit cell, but they are both carbon atoms and it's interchangeable. However, it is important that there are two, and that they're called A and B, as we will see as we develop the quantum mechanical model for graphene. Okay, so we have figured out what is the lattice. It is a trigonal lattice, and now atoms A and B are marked with blue and yellow colors. We can define vectors of this lattice, primitive unit vectors, and they will be vectors A1 and A2. They start with the lattice site, and we connect to the nearest neighbor site. So this will be a basis vectors. And they can be written out like this. Because it's a hexagon, there will be the square roots of 3 from the sines of 30 degrees. A will be the distance, the size of the hexagon. So that's about 1.42 angstroms. That's the size, the distance between the two atoms. So the length of A1 and A2 are given here in terms of A. And you can see that these are not 90 degrees with respect to each other. They are unit vectors of a trigonal lattice. And therefore, they are at this angle of 60 degrees. Okay. We can also construct a reciprocal space. So we need to remember the formula that includes the vector products of A1 and A2. And the third vector for that formula, we can take it just perpendicular to the plane. The Z vector, the third vector for that formula to work, can be a unit vector perpendicular to the plane. And we can derive B1 and B2, which are the reciprocal lattice vectors. And you can see that here we have 2 pi over A with respect to this, and also they form their own trigonal lattice. So in reciprocal space, again, we have a trigonal lattice. And you remember that it is important for the band structure calculations to know what is your Brillouin zone. Now, a Brillouin zone, we can construct it by Wigner-Seitz method, which is to find the region around the reciprocal lattice point, the region in space for which this point is the closest lattice point to any point in that region. So here is the next lattice point here, here's the next lattice point here, here's another one here, and then we just go along the line connecting to lattice points and make a cut halfway. And we repeat this for all directions around. And we find that it's a hexagon. So the first Brillouin zone is the space inside this hexagon. Gamma is the name of the point in the center of the first Brillouin zone, as we already saw before. So that's a k equals 0 point. And interesting points that we're going to be wanting to look at are these k and k prime points. K and k prime points will play a huge role in the graphene band structure. I will tell you a little bit later on why they're called k and k prime and what's the difference between them. Okay. How are we going to find the band structure? We can use a tight binding approach. You remember a tight binding approach? You allow for coupling between the lattice sites, and you also have some energy of being on a lattice site. And then from this, you build a wave function, assuming some ansatz, which includes the orbitals. So eigenstates of an electron on one particular lattice site, on one particular atom, are called orbitals. And then you hop from one orbital to the next by some tunneling J. before, when we considered this tight binding model in its pure form, in its conceptual form, we just introduced J as is. Now we have a particular lattice of particular atoms, and so we are going to build J in a little bit more detail. So J will emerge from this calculation. So this is a tight binding approach, but I'm not going to just say J is equal to 1 electron volt or something like this. I'm going to construct it based on this lattice and based on the wave function given by this ansatz. So this is a collection of plane waves. This should be you should be comfortable with this kind of construction from previous examples. And this includes a k vector. R are the vectors in real space, so they belong to G, which is, I guess, the graphene lattice. That's what it means by G here. And there is this function, which comes from the orbitals. Okay. So what is this function phi? We are going to say that it is a function that includes a probability to be on atom A or probability to be on atom B, which are going to be phi 1 of x and phi 2 of x. So these two functions will have peaks at the position x1 of the first atom and a position x2 of the second atom. In fact, you can see from this construction that this function is built in k-space and that you can be on anywhere on a real lattice. This sum goes over the entire lattice. It tells you that actually these coefficients B1 and B2 tell you how much of your electron lives on one sublattice, on the A sublattice, or on the B sublattice. So you just look at the blue points, and that's one sublattice, and that corresponds to B1. And you just look at the yellow points, and that's another sublattice, and that's a function B2. So but that's also a very natural ansatz for us, because we know that we have a unit cell with two atoms, and so this corresponds to having a lattice with a basis of two atoms. Probability to be on one atom and on the other atom in a unit cell is given by B1 and B2. And so, like I told you, we start a little bit back to arrive to a tight binding model, and therefore we consider this Hamiltonian, which is just a Hamiltonian of an electron living in the graphene lattice. So it has the free particle component and this potential which confines the electron either to an atom at position x1, that will be atom A, or atom at the position x2, that will be atom B. And this potential repeats itself with the periodicity of the lattice, which is given by these vectors R. And of course, this potential has some kind of an extreme point at x equal to x1 or x equal to x2 for that other term. So what do we need to solve to find the band structure? Very fundamentally, we need to solve the Schrödinger equation. And so we have to take the wave function and plug it in to the Schrödinger equation, find E of k, find our dispersion relation, and those are going to be our bands. That's what we're going to do. Now, I already showed you before that you can represent this Schrödinger equation as some kind of a matrix, right? Where you have, inside this matrix, you have matrix elements which are on the diagonal, the eigenstates of some Hamiltonian, and off diagonal, there are transitions between different states. And in this case, for the basis of this matrix, we can choose the probability to be either on sublattice A or sublattice B. So we are going to project it on these phi functions here. And in this form, if we project this Schrödinger equation onto the phi functions here, we need to calculate various matrix elements. For example, we need to calculate matrix element between phi 1 and phi 2 and the full wave function psi. And we also need to calculate the matrix element of this Hamiltonian for function phi and psi. So if you project this Schrodinger equation onto phi 1 and phi 2, you're going to get two equations of this form. And why are we projecting it? So that we can build this matrix. And then it will be very easy to solve the Schrodinger equation because we just need to diagonalize this matrix. And that's going to give us the energy bands solution. Right? So this is why we're doing this. But what we need to do is to calculate this matrix element and this matrix element. Now, what is this delta U? Delta U just comes from applying this Hamiltonian to the wave function phi. So it contains this V atomic for x1 and x2. Okay, so this is a bit of a lengthy expression to carry this H around, and so it's replaced by delta U in this math. Okay, so our plan is to look for a solution in this form, where phi is given by a combination of being on sublattice A and sublattice B, and then solve a Schrodinger equation, which we rewrote in projection to phi 1 and phi 2 this way. That's going to create a matrix, 2 by 2 matrix, which we diagonalize and find the energy solutions. This is just our way of solving the Schrodinger equation. Here we calculate these matrix elements that we need here. So if you look at psi and phi, to take the matrix element between phi and psi, right? Remember, this is an integral of phi, psi, dr over the entire space. That's what the matrix element is. If you take an integral of phi times phi, that's going to be 1 because all the wave functions are normalized, and the probability to find a particle in the wave function integrated over the entire space is 1. Therefore, if you take psi with phi, the matrix element of that, you're going to get from phi 1, you're going to just get B1 here. So phi 1 and psi going to give you B1. And from phi 2 here, you're going to have B2 times the integral of phi 1 and phi 2. Right? So you plug in this phi into the psi, and then take a matrix element between them. So you're going to have the integral of phi 1 and phi 2. And you're going to have this term, which we should discuss in a bit of detail. This is where the tight binding approach begins to kick in. So this term comes from e to the ikr here, from this ansatz that we've made, that these are plane waves living in a tight binding potential, in a periodic potential. For it to be tight binding, we're only going to include for today the nearest neighbor terms. All the others are going to be 0. So electron cannot hop from a yellow atom all the way here. It can just hop to the nearest atoms. And what this creates for us is we have to substitute for r just vectors a1 and a2. That's what we have to substitute for r. And that will create 3 terms here. One is unity, because that's just the position of atom itself. And then IKA1 and IKA2. So that's going to be a very important prefactor here. So we have a very similar expression for the matrix element of phi 2 with psi. So if we take integral of here phi 2 with psi, we're going to have B2 because of the integral of phi 2 and phi 2 in the psi. So we're going to have this B2, and then we're going to have B1 times the integral of phi 2 phi 1, and the same prefactor with different signs here. Okay, so we're going to go forward by calling this integral here gamma 0. And we're going to say that both of them are the same, gamma 0 here and here. So phi 1 complex conjugate phi 2 is the same as phi 2 complex conjugate phi 1 because this integral is real. So we're going to have them be the same. We are going to see that we're going to call this prefactor alpha. This is just not to carry these expressions around. Okay, so we've calculated the matrix element of psi and phi I. And our Schrodinger equation was also including phi delta u psi. So we need to calculate this term, which is the transition from one sublattice to the other over the confining atomic potential. So if we do this calculation, we're going to find an expression which is very similar in structure because the integral of phi 1 with phi 2 will be some number. It will be gamma 1, for example. But the integral of phi 1 with itself, with phi 1 over this Hamiltonian, will actually be 0, because this Hamiltonian corresponds to a transition between atoms. And therefore, this expression just has B2 and gamma 1, which we abbreviated this integral with, and another prefactor, which is the same as for the other calculation, which we called alpha. And so by doing this, basically taking these matrix elements between phi and psi with atomic potential, we reconstruct Schrodinger equation in the matrix form, like I promised to you. In this case, we already moved E of k from the right to the left, and the matrix equation is just this 2 by 2 expression here. This is the Schrodinger equation just expressed in terms of the parameters that we introduced, gamma 1, alpha, and gamma 0. And we need to solve for E of k. How do we solve? We find a determinant. So this term times this term minus this term times this term equal to 0. And we can just find E of k by solving that equation. That is just essentially a quadratic equation. Okay, so it's a little tedious, but this is the solution. So this is the solution of the tight binding Schrodinger equation for a graphene lattice, for a hexagonal lattice. This is what it is. Now we already plugged in A1 and A2 here, pointing this way, and that's why you have Kx, Ky here, and A, which is the lattice constant, the distance between atoms, sorry. And you have gamma 0 here, the integral that we've calculated before, also in this expression. Now, you can plot it. This is what you're going to get. So this is a plot in K space of the energy bands. Because it's a two-dimensional material, a truly two-dimensional material, we can conveniently plot it in 3D and use the third axis for energy. So you have Kx, Ky, and the third axis is energy. And you have this magnificent structure, which is just this solution here, given here. It has two bands, thanks to this plus minus here. That's plus minus, gives you two bands. Why do we have two bands? What determines the number of bands? Right, number of atoms in the unit cell or number of orbitals available per unit cell. Right. In this case, each atom has one pz orbital, and we have 2 atoms, so we have 2 orbitals per unit cell. So a tight binding calculation should give us 2 bands. Should give us 2 bands. And there is a band gap. So you can see this hollow region around here, that there are no states, the bands are repelled. It's a band gap. But there is also something very peculiar and rather unique to graphene, is that there are these 6 points where the bands cross and they don't repel each other. There is no band gap opening at these points. And those are the K points. They are K and K prime points. They are the corners of the Brillouin zone. So at these corners, remember I told you at the edges of the Brillouin zone, what all these models give you, the tight binding, the free electron, near free electron model, that at the edges of the Brillouin zone there is a gap opening in the spectrum. Well, in this case, in these particular 6 points, it is not happening. And that's because of that factor alpha k, which had 1 plus e to the I e to the I ka and so on. So it's thanks to this factor alpha, at those points, there is a cancellation of this interaction term between the bands, and the bands become degenerate at those points. However, in the middle of the Brillouin zone, which is this gamma point here, there is a huge difference between the bands. And that's because of the, you can think of it as a bonding and the anti-bonding orbitals between the two atoms of carbon. Okay, so here upstairs is the picture from before. I need to erase some stuff. Oh, it erased itself, great. Here is a picture from before, and here is just a cut through it, a simplified view, which makes things clear. So this is a cut going from gamma to k, from gamma to k point to one of these degeneracy points. If you cut across there, you will see the 2 bands, the blue and the red, and you will see that these 2 bands, they cross at the k point, and they make this degeneracy here. There is no energy gap at k points. If we now look from the top at the band structure, we will see the Brillouin zone like this hexagon. Those are the k points. And remember I told you that there are k points and k prime points. So the difference between them is that they belong to 2 different valleys of graphene. They are not equivalent. What does it mean that the k and the k prime are not equivalent? It means that if you are sitting at this k point, you cannot come up with any reciprocal lattice vector g that will bring you into the k prime point. So if you sit here and you go by g in any direction, g, 2g, 3g, minus 3g, in any direction, you will always hit another k point, and there are 3 k points in the corners of the Brillouin zone. And then there are 3 other points, which are called k prime, that you can never reach by going by reciprocal lattice vectors. So you can never reach those points. And that's why these 2 are not equivalent. And that would mean that there are 2 valleys in graphene. That means that the electrons in one valley, in principle, cannot cross into another valley unless we allow for some additional physics mechanisms for them to do that. Okay? In this pure calculation, these 2 valleys are separate. So it's like 2 seas of electrons living in the same space but not seeing each other, like there is a parallel world of ours. Okay. Now, these points, these K points, are the main focus of graphene research and what makes it extremely interesting. This is why. So the gap is 0 there, essentially. It means that the valence and conduction bands meet together. Why is that? It's because we have 2 bands in graphene, and we have 2 electrons per unit cell, right? Each of the pz orbitals has 1 electron. But remember, we have spin up and spin down, and that means that only one of the bands is fully occupied, and the other band is fully filled. So if we had a band gap, we would be in a semiconductor situation where all of these states would be filled with the 2 electrons per unit cell, and all the states above will be empty. So this would be the conduction band and the valence band, and we are in a semiconductor scenario here. Now, in graphene, what we have is all of these states are filled. However, all of these states are empty, but there is no gap between them. You can take an infinitely small energy and go between the valence band and the conduction band. So graphene, by our definition, is then a metal. Graphene is a metal because of these K points. There is another very, very interesting thing about this band structure in graphene is the shape of dispersion relation. Whatever we looked at so far always had a parabola dispersion relation, like is shown here. This is for the conduction band and for the valence band. I told you at every band minimum, we can expand the band structure to be a parabola around the K point, which is the band minimum. Now here is the band minimum, this red point, but it's not quadratic. It is actually linear. So this dispersion relation is linear. It's given by this formula. Energy is proportional to momentum. So who can remember another particle for which this is the case? The photon, right. For a photon, you have a speed of light times momentum gives you energy. And this is this is not a photon, this is a fermion, this is an electron, but it has a dispersion relation of a photon. So another object that has this dispersion relation is a relativistic electron. So the electron traveling at very high velocities close to the speed of light would have this kind of dispersion relation. And those electrons are solutions of a quantum mechanical Dirac equation, which is a form of Schrodinger equation for an electron. And for this reason, this kind of band structure is called a Dirac cone. And this Fermi velocity in quote marks is kind of like the speed of light for electrons in graphene. It is much slower than the speed of light. This is what it actually is. This is a parameter you can calculate from the band structure. You can actually tell what this slope of this cone is supposed to be. This velocity is, plays the role of the speed of light. So this is why people say that they study relativistic electrons in graphene without needing to accelerate electrons to extremely high velocities. They're automatically traveling at this graphene speed of light velocity. So conceptually, it's very interesting, and it gives rise to a lot of interesting physics phenomena, like, for example, tunneling through the barriers without retroreflection, which is called Klein tunneling. Don't have time to explain it to you today, unfortunately, but I encourage you to look up Klein tunneling in graphene. Something that was envisioned for relativistic particles, but could not be observed with real relativistic particles, but in graphene is possible. Now, the meaning of this VF is also that no matter what the energy level is in this band structure, you can raise the chemical potential and fill part of the conduction band, or you can be in the valence band. But no matter where you are, these particles travel with the same speed. Whereas in a more standard band structure, Of course, the more you fill the band, the higher the kinetic energy, the larger the momentum, the larger the velocity, because velocity is just a derivative, dE dk, right? Here dE dk will change with p, and here dE dk is independent of p. So these are some of the bizarre and interesting consequences of having a linear dispersion relation like you have in graphene. Okay. That's what I wanted to tell you about graphene today. There is a lot more to discuss, and I wish I could tell you more. But let's look at something else where we can put our knowledge to use, and it's a carbon nanotube. Carbon nanotube is a tube of carbon atoms, and how you get it is by taking a sheet of graphene and rolling it into a tube. Okay, this is not how actually you do it. Right? Nobody actually was able to take a sheet of graphene and roll it into a tube so far, although people were able to unzip a nanotube. They took a nanotube and cut it and made a little piece of graphene out of it. That was possible chemically, but not the other way around. But conceptually, this is what you do. So for example, here is a graphene sheet, and you can imagine taking a cut like this, and now taking atoms from the bottom and making bonds, right? So now atoms on the corners have only 2 bonds, the yellow ones, and the yellow ones here have 2 bonds. And you take the atoms with 2 bonds and connect them with the atoms with missing bonds on the other side. And they become happy. Each of them has 3 bonds, 3 sp bonds, and of course 1 p orbital sticking out. And you make this object with all the chemical bonds satisfied and the p orbitals available for traveling around. So this particular one, the nanotube you make this way, is called an armchair nanotube. And the reason why it's called armchair is because the edge looks like this, and it reminded somebody of an armchair. Okay. Not my choice. I would have called it, I don't know what. But this is not the only way that you can roll a piece of graphene and make happy bonds with atoms on the other side. In fact, there is a huge number of ways, and in principle, an infinite number of ways to roll graphene. An armchair way is only one of them. More generally, the way you roll it is by defining a rolling vector, which is n times going along vector a1 from graphene, right? The a1 and a2 are these little vectors here, which are the primitive lattice vectors of graphene. Going n times along a1 and m times along a2 will always give you a nanotube. So here is a general example where the equivalent points on the nanotube are the red points here. So this is how it's going to be rolled. This is the vector c in this direction. So this is a vector c mn. Now this vector is a vector t, and this is a vector of translation along the tube. So there are 2 natural ways for an electron to travel in the tube. One is to go around the tube, and there vector c is the important one. It's the roll vector, where you start with this point and you end up at the same point after you traveled for vector c along the circumference. And the vector t is just traveling along the nanotube. So a nanotube is an example of a one-dimensional molecule, one-dimensional solid. So it's a real one-dimensional structure because electron can live, the wave function of the electron can live in the entire circumference, and occupy the entire nanotube in this direction, and then can travel as a particle along the tube. So the third direction is free, and this direction is confined. And we already confined in one direction because we are on the graphene sheet. Now, the gray region here is the unit cell of a nanotube crystal. So depending on the vector C, it can be a pretty huge unit cell, right? All the atoms of carbon that are in the gray area are inside one unit cell. So there can be something like n times m atoms, or of that order. So there are a lot of atoms in a unit cell, and that means we're going to have a lot of bands, right? Because each of them brings a band. So that all makes sense, right? So it's also reasonable why the unit cell can be so large, right? Because we, to define a unit cell, we want to start with a lattice point and then end up on another lattice point. And so for this reason, you have to travel by vector t to hit another carbon atom. There are no other carbon atoms in the path here until you reach this one. That's why this is the size of the unit cell. And in the direction of rolling, in the C direction, it's obvious. This is, anywhere you are on a nanotube, it's very different. So you have to go all the way around to complete the unit cell. And so then nanotube is built by stacking unit cells like this on top of each other. So the next unit cell will be here. Well, this is actually the size of 2. So they will go up and up and up. And the dashed line on the other side will be the same as the... Make sense? So these are some common examples. We already know the armchair tube. Actually, it's a bit confused here. This one is the armchair. This one is the zigzag. So a zigzag is a tube where you can trace these kind of line along chemical bonds. And so it actually turns out that to make an armchair tube, your C vector has to have NN, has to have the same indices for A1 and A2. So this means the C vector is N times A1 plus N times A2. So you go like that through the graphene. And for zigzag, you just go in one direction. So I think this is also confused here. Okay. And then you can also have an arbitrary kind of tube, which is then called the chiral tube. So then you have M and N different indices. And why it's called chiral is because you can see the lines are tracing through the tube like this. So it wraps. The sheet of graphene wraps like this. Okay. So this is the nomenclature. Now, what are the consequences of this wrapping and periodicity for the band structure? The general approach we're going to have is we're going to say this is essentially graphene. This is a sheet of graphene just rolled up. And what does this rolling up give us? It gives us a periodic boundary condition on the K vector. So we're already familiar with boundary conditions. We saw that when we have a finite size crystal, we only can occupy discrete K states. Remember, we have a continuous band that we obtain from a solution of some model, like the tight binding model. But we also have to remember that we have only n unit cells in this crystal. And that means that only n points in this band structure are allowed K vectors. And in fact, what we used to derive these endpoints were periodic conditions, even though that was maybe not the most physical thing, because the crystal is not a periodic crystal, meaning that one end does not connect to the other. Electron traveling this way does not appear on the other end. But the result is always the same, regardless of boundary conditions. But in this case of the nanotube, we actually have periodic boundary conditions. You travel around the loop and you arrive to the same point. And so before we looked at these Born-von boundary conditions, which told us that the allowed k values are some integer divided by the number of cells in the crystal in the directions n1, n2, and 3, and only these values for m1, m2, m3 integer are the allowed k vectors. In the case of graphene and carbon nanotubes, we have two things going on. We have travel along the circumference, and there we have a periodic boundary condition. And we have free travel along the other direction. So what that's going to do to the graphene band structure, I showed you these points here that are the allowed points. Now we have this two-dimensional band structure, and periodicity in one of the directions will reduce this two-dimensional picture to one dimension, where the allowed k values will be given by the red lines crossing through the band structure. So these cones here are the 6 Dirac cones zooming into this region. And now looking at them at an angle, we can see that the yellow is the occupied, so the Fermi level is at the 0 energy and all the states below are occupied. The white halves of the cones are not occupied. And now, because we are in a nanotube, only states along the red lines are the allowed ones. That's due to the periodic boundary condition. And that's expressed in this form in terms of vectors T1 and T2 for the graphene lattice. So now that's very interesting. Depending on how the nanotube is rolled, the slopes of these red lines will change, and they will go through different points in k-space. So imagine that none of these lines hits a k point. None of them hits this point where the gap goes to 0. That means for any allowed value of k, there is a gap, because in the graphene structure there is only one point where gap goes to 0. That's the k point. So if these lines don't cross the k point, there is a gap. And so by creating a carbon nanotube, we essentially gapped graphene. So graphene was not gapped. Graphene always has these Dirac cones where the gap is 0. But the carbon nanotube will be gapped. But not always, depending on the rolling vector. So here are the gray shapes, which are the Brillouin zones, and the k and k prime points are the corners of the zones. And remember, you need to hit one of the corners. And if you hit one of the corners with a black line, which represent the allowed values of k, so black lines are where k's are allowed by the periodic boundary conditions. If you hit a boundary of the Brillouin zone, then you have no gap. And your tube is called a metallic tube, because you are crossing the Dirac point. And so for the armchair and the zigzag tubes, it happens to be the case that you hit k and k prime points in this case, and k points in this case. So for these particular rolling vectors 10, 10, you're going to have 20 states, I believe. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. 20 states, so it's 2n. And you go through one of the k points. That means there is no gap. It's a metal. Now for zigzag tube, which is going this way in one diagonal cuts, you also hit one of the k points. And so there is a band which has no band gap with the other band. So that's also a metal. This is some kind of a different zigzag tube with 11, 0. So this is 12, 0. This is 11, 0. So both are zigzag, but slightly different rolling vector length. And in this case, you actually don't hit any K points. So in the zigzag case, you can be a metal or a semiconductor. So if I project this onto the energy axis, this is the energy axis, and this is some K, where here is my Dirac point. The allowed values of K can be including the Dirac point or not including the Dirac point. And that makes a difference between it being a metal or a semiconductor. Now you can work out for all possible rolling vectors whether you're going to have a metal or a semiconductor. And it turns out that there is a general formula that when the rolling vector satisfies this expression, 2n1 plus n2 or 2n plus n is a multiple of 3, then you have a metal. This is just, you can work it out from looking at the band structure of graphene. And if you put this equation to a visual representation like this, then if this is a point 0, 0, then these are all possible rolling vectors that you can have. They stop at this line because they will be equivalent. If you cross this line to the bottom, you will find the same nanotube, basically, as one of these if you go in this direction, due to the hexagonal symmetry of the graphene lattice. So this is the armchair tube along this vector. Along this vector, it's a zigzag, and all these in between are chiral. And then the filled circles are semiconducting tubes, and the open circles are metallic. So along the armchair edge, you can see that they are all open circles. Always you're going to hit a K point along the armchair direction. And along the metallic zigzag direction, you have a mixed metal or semiconductor situations. Oops. So this is the difference in the band structure, what I was trying to explain with these cuts. So each of the cuts gives you a band. You have a two-dimensional graphene band structure. For each of the cuts, you can plot how energy evolves along that cut, and then you can plot them all on top of each other, because in the reduced zone scheme, all the bands will live in the same Brillouin zone. Now we have a one-dimensional Brillouin zone because of this additional quantization condition. We live along these cuts. And when we have 20 cuts, like in this case, that means we have 20 bands. And some of the lower bands are represented here. So when you include a K point in one of the cuts, and you go along that cut, you're going to see a linear dispersion relation close to the K point. And that's going to be a metallic tube. If your cut goes a little bit off to the side of the Dirac point, of the K point, your lowest energy band is going to look like a parabola. Why is that? Because here is a cone. And imagine that you are cutting the cone with a slicer a little bit off of the center of the cone. If you cut it a little bit off of the center of the cone, you're going to have a slice that looks like this. You cut it here. And that will be this red band here. That's the slice that I just showed you. Right? But then you have these, you slice up the cone with 2 times n bands, and you're going to have 2 times n slices, and they will all go to higher and higher energy as you move away from the cone. You line them all up, and this will be the band structure of the nanotube. So statistically wise, armchair is always metallic. Zigzag is 2/3 metal and 1/3 semiconductor. Chiral are same ratio. It is actually a little frustrating from the experimental point of view because you may want a nice metallic conducting nanotube for building an electrical experiment, or you may want a nanotube with a gap for some other device like a transistor or some optical device where you want to excite photons across the gap. But when you grow nanotubes, you normally don't control this N and M. You don't control this chirality. You grow 1,000,000 of them, and they will all wrap how they please. And so some, 2/3 of them will be metallic, another third of them will be semiconducting, and the one you take will have this probability. You will not know. So people are actively researching ways to select them based on chirality, and there is some progress in this direction. So that will be a great advance for nanotubes because they are, of course, proposed in all kinds of applications. So this is the general formula for this band structure. So I told you, you slice up the Dirac cone. This is the energy band structure for an arbitrary nanotube. You can see that it's an energy versus k parallel. K parallel meaning momentum along the tube. That's where you are not confined. K perpendicular is confined. So different values of k perpendicular give you different bands in a nanotube. So this is as a function of k parallel. M and N are the components of the rolling vector. And this index P just enumerates the bands. So that's just an integer that enumerates the bands. So you can get for any chiral nanotube a band structure based on this formula. The values of k are restricted. K perpendicular are restricted to these numbers. You cannot have any other k perpendicular due to the periodic boundary conditions. And these are some examples of calculations using that formula for different rolling vectors. And once again, you can see that sometimes you have no gap, sometimes you have no gap, sometimes you have a gap, depending on numbers N and M. Okay, I think that's where I'm going to stop today, and I'll see you on Thursday.